Okay, so now I want to talk about the idea of neighborhoods. And later on, I'm going to get onto the notion of connectedness in topology as well. So, a neighborhood is basically another kind of simplifying concept which goes together with the ideas of open sets, closed sets, and limit points to give yet another equivalent way to describe the topological properties of a space. So I'll define a neighborhood precisely. So let X tau be a topological space. Now, a subset M of the space is called a neighborhood of a point P in the space when we have that there exists an open set U such that P is a member of the open set U, and the open set U is contained within this set M, which we're calling the neighborhood. So we can just draw a little diagram to illustrate what's going on here. So if this is our space X, and this is our neighborhood N, and so this will be a neighborhood of a point P. Whoops. Excuse me. Where this will be a neighborhood of a point P when there exists an open set U which contains P and is itself contained within N. Okay, so a very simple concrete example. Suppose we have the Euclidean topology and we have the number 2 in the reals. So a neighborhood of this point 2 would be the interval from 0 to 4. The reason is because this contains open set, the set of all numbers greater than 1 and less than 3, and this open set contains the number 2. So the interval of all numbers greater than or equal to 0 and less than or equal to 4 is a neighborhood of the point 2 because there's an open set which is contained within the neighborhood and contains point 2. Okay, so a fairly important observation is that every single open set is going to be a neighborhood of every point inside that open set, because if you take any open set, take a point inside it, so take an open set U and a point P inside it, then U itself is an open set contained within U, which contains P. So U is always going to be a neighborhood of the point P. And also, another important thing is that if you have a neighborhood of a point and you take a superset of that neighborhood, that is, a set which contains that neighborhood, then that superset is also going to be a neighborhood of that point. So this is really quite a malleable notion. And we have the following proposition. Which is fairly easy to prove. I'll leave it as an exercise for you to prove it. You'll be able to do it by looking at the last lecture and using the definition of limit points. So the proposition says if we've got a topological space and we have a subset A of that space, then we're going to have that a point in the space is a limit point of this set A if and only if every neighborhood of X contains a point of A other than X. So notice that this is almost identical to the definition of a limit point. It's just that we've replaced where we say the open set with the word neighborhood now. So there's a couple of fairly interesting kinds of implications from this proposition. So in particular, it gives us a new way to specify when a particular subset of a topological space is open or closed. So I'm going to give some corollaries to proposition A. Okay, so our first corollary, corollary B is going to be that, okay, so in general, we're just going to imagine that we have some subset of our topological space. That'll save me having to keep writing things out. So A is just some subset of the space. And now our first corollary says that A is going to be closed precisely when we have that for every point outside of A, there exists a neighborhood n of X, which is such that n is contained within the complement of A. So a set is closed when every point outside it has a neighborhood which doesn't touch it. Okay, and this seems kind of intuitive to our idea of what a closed set should be. It sounds right. And it follows directly as an implication from proposition A. Again, I urge you to try and prove this. Okay, so another consequence then, carrying on the chain of reasoning, we'll call it corollary C, is that if we have our subset A, then it will be open precisely when for every point in A there exists a neighborhood n of that point which is such that that neighborhood is entirely contained within A. So again, this is very familiar, this kind of notation. And then there's a consequence of corollary C, which is a very useful test for when a set is open or not. So I'll just write it up here. Whoops, but not delete that. I'll leave the red writing up there. So corollary D, another necessary and sufficient condition for the subset being open is that for every point in the set A, there exists an open set which is such that X is contained within the open set, which is contained within A itself, which looks remarkably similar to the definition of a neighbourhood. So this is a nice test for if a set's going to be open or not. Okay, so now let's turn to the idea of connectedness. And to do this, we're going to start by thinking about open sets in the Euclidean topology. So we'll do this with what I'll call lemma E. And this is as follows. Let S be a subset of the reals which is bounded above and let P equal the supremum of this set. In other words, P is the least upper bound. I better just point this out, this notation, just in case people haven't seen it before. So it means least upper bound. A couple of examples. The supremum of the set from 0 to 1 is 1 because it's an upper bound and it's the smallest one. Also, if we take the open set, the numbers strictly between 0 and 1, again the supremum is equal to 1, even though it's not actually in the set. So there we are. We've got, so far in our lemma, we've got this subset of the reals, which is bounded above, and P is its supremum. And now what our result states is that if S is closed in the Euclidean topology, then we're going to have that P actually belongs to the set S. So it's kind of just like in this case, actually. This is a closed set here, and in this case the supremum does indeed belong to the set. But this lemma says that this always holds for any closed set under the Euclidean topology. So there's a nice simple proof by contradiction to this result. So here it goes. The proof is as follows. So suppose we've got this closed set. Now we're going to do a proof by contradiction. So we're going to, rather than supposing that the supremum P is inside the set, let's suppose that it's outside. So P belongs to the complement of this set S. Now this is going to be an open set. This is open, right? And so what that means is, it means that there's going to exist an A and a B such that this supremum point P is going to belong to this open interval between A and B. And this open interval is going to be contained within this open set, which is the complement of S. And now we've already got a contradiction, okay, because we have that A is less than P, and A is going to be an upper bound on S, because it's outside of S. And so this is a contradiction because P is supposed to be the least upper bound, but A is less than that. Before I state the definition of a connected topological space, I want to establish this next proposition, proposition F, which is going to motivate our definition because it's going to show us what the word connected means in terms of the Euclidean topology. So what this proposition says is if we have a Clopen subset of the Euclidean topology, so remember this funny word Clopen means open and closed at the same time. Well then, there's only two possibilities. Either this Clopen subset T is going to be equal to the set of all reals, or it's going to be empty. It can't be anything else. So the proof to this is quite elaborate, but I'll go through it because it's fairly important. So it's a proof by contradiction. So we're going to suppose that this result's not true, and suppose that our Clopen subset of the reals is not equal to the set of the reals, and it's not empty. Now we're going to try and derive a contradiction, which will mean that our original supposition was false, and so indeed the proposition must be true. So here we go. So if T is not equal to the whole space and it's not empty, then there must exist an element X in T because it's not empty, and there must exist an element Z which is in the complement of T because it's not equal to the whole space. And without loss of generality, we can just assume that X is going to be less than Z. Okay, so what we're going to do now is we're going to define S as a new set. It's going to be equal to the intersection of T with the closed interval from X to Z. So let's just draw a little diagram to help us here. So of course we don't know what shape, we're not really assuming what shape T has, but just for the purposes of a simple diagram, I'm just going to draw it as a line. So say this is T. Now what we're supposing is that we've got a point X in T, so there's X, And we've also got a point Z outside of T. Oops. And we've got this interval, this closed interval between X and T. And S is going to be the intersection of this T, this black line, with this red interval between X and T. So this is going to be S. Whoops. Okay, so that's the situation. Right then. So S is going to be closed. Why is S closed? Well, because it's the intersection of two closed sets. Remember, T is both open and closed, and of course this closed interval between X and Z is closed. It's also bounded above, and so we can let P equal the supremum of S. So let's draw that on our diagram. There's our point P. Now then, by lemma E that we just established, we've got to have that, in fact, P is a member of S because it's a closed set. Now also we have that P, hang on, right, so I want to keep this on the same board, so I'll delete the proposition. And let's just restart our conversation up here. Okay, so since this point P has got to be between X and Z, because it's inside S, P's obviously got to be less than or equal to Z. And also, the thing is that since Z is outside of T, by definition here, Z's got to be outside of S because S is just the intersection of T with the closed interval. So we must have then that Z belongs to the complement of S. And so this together with, let's do it in blue. So this together with this gives us that actually we must have that P is strictly less than Z. Okay. Right, so now let's do the next part of the proof. So we're about halfway there towards deriving our desired contradiction. So now we're going to think about how T is open. So P is in T, and T is open. So there's got to exist A and B such that P has got to be in the open interval between A and B. So let's put that in our diagram. Not sure what colour to use here. So there's got to exist an open interval containing P. And what we're going to do now is we're going to let T be such that P is less than T and T is less than the minimum of B and Z. So if Z is less than B, this is equal to B, otherwise it's equal to Z. Okay, so clearly then we're going to have that this value T, little t, is going to have to be a member of our space big T, and also little t is going to have to be a member of the interval from P to Z. And so what that actually means, putting this all together, is that T is going to be a member, so we're pretty much there now, T is going to be a member of capital T intersection XZ. And what is that? That is just equal to S. So now we've got our contradiction, because T is going to be actually greater than P. So there's no way that P is the supremum of capital T. Sorry, there's no way that. So we've also got that P is the supremum of S. So this doesn't make any sense, because we've just found a point T in S which is bigger than P, so there's no way that P could have been the supremum of S. So we have a contradiction. Okay, so basically our notion of when a topological space is connected is pretty much the same as the thing we just encountered in proposition F. So let me now, at long last, get to the definition of a connected topological space. So basically, a topological space is connected precisely when the only Clopen sets, the only sets which are simultaneously closed and open, are the entire space X and the empty set. There's nothing else in there which is both open and closed. So an immediate implication of this and proposition F is that the real line is connected, because we just proved that the real line has exactly this property. Now, I think a more familiar kind of way to state this result, so that you can see why this really means connected, can be given as follows. So when a space is not connected, we call it disconnected. I know that's pretty obvious, but I might as well just write it down for the sake of definition. So when x tau is not connected, we say it's disconnected. Okay then. So what we actually have, I'll leave this to you as an exercise to prove it. This is a nice little result. We have the topological space x tau is going to be disconnected precisely when there exists some non-empty open sets A and B which have the property that they have an empty intersection, so they don't intersect, but the union is the entire space. So this is also basically what's called a partition, and sometimes in many books they actually use this as a definition of connectedness. I think it's probably a more natural way to think about it. They use this to define connectedness. So basically a space is disconnected when you can partition the space into two open sets which don't overlap. You see what that means then is that if you look at A is open, and then the complement of A is going to be B, which should be closed, but B is also open, so both of these sets are Clopen. And if you think about limit points and things, you should start to understand why these things are considered to be disconnected.